This lesson is entitled Exploring Real Numbers. The real numbers system is a set of numbers of all the possible numbers that we could actually study. The real numbers aren't all the numbers we could study, but they're the first group of numbers that we study in high school mathematics. The real number system is split up into two categories. We have the rational numbers and we have the irrational numbers. Rational numbers are any numbers that can be written as fractions. For example, 2/3 is obviously a rational number because it's written as a fraction. These fractions have to have whole numbers on the top and the bottom. We don't want to see decimals or other fractions inside our fractions. We want to simplify it all the way to just one whole number over another whole number, or one integer over another integer would be a better way to say that. Irrational numbers are numbers that can't be written as fractions. A good example of that would be the number pi. In the rational numbers, we have our integers. That includes, for example, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, and then off in both directions. Inside the integers, we have what are called the whole numbers. The whole numbers just start at 0. There's no negatives. 0, 1, 2, 3, 4, 5, etc. Those are the whole numbers. And inside the whole numbers, we have what are called the natural numbers. If you ask any little kid to start counting, they all start at 1. They just naturally start at 1 and say 1, 2, 3, 4, 5. So we call those the natural numbers. We have some vocabulary that we need to make sure we have down as we study these numbers. Absolute value. Absolute value is defined as a number's distance from 0 on a number line. It's always positive. That's a key thing. Remember, the absolute value is always positive. Opposites. Two numbers that are the same distance from 0 on a number line, but lie in opposite directions. For example, 5 and -5. They're 5 away from 0, but they're the same distance, 5 away from 0, but they're on opposite sides of the number line. An inequality is a mathematical sentence that compares the value of two expressions using inequality symbols. The inequality symbols we should be familiar with are the less than and greater than, and we also have the or equals that we can throw on either one of those. A counterexample is any example that proves a statement false. For example, if somebody stated all real numbers are even, and all you'd have to do is say, well, 3 is a counterexample. There's a real number that is odd. It's not even. Try this. Are whole numbers, integers, or rational numbers the most reasonable for each situation? So shoe size, are all shoe sizes whole numbers? Are all shoe sizes integers? Or are all shoe sizes rational numbers? Well, I wear a 10.5, and that's not a whole number. It's not an integer, but it is rational because 10.5 can be written as a fraction. So those are rational numbers. How about the number of siblings, the number of brothers and sisters that you have? Well, hopefully you don't have a fractional part of a brother or sister. Hopefully that's a whole number. You don't have any negative. Well, you might have some negative brothers and sisters, but a negative number of them. So therefore, those would be whole numbers. Temperature in a news report. I had never heard the news guys say the temperature is 76.2. We might see that on a reader board somewhere or something, but they'll use integers. We can actually see negative temperatures when we get below 0. So that would include the integers, not just the whole numbers. Number of students in a class. Well, again, you could have 0, you could have 1, you could have 2, hopefully up to not more than 30 students in a class. That would be whole numbers again. We won't have negative numbers. We won't have fractional parts of students, hopefully, in our class. So whole numbers. I'll go a little slower on this, and you try to say what the answer is before I do. The number of quarts of paint you need to buy to paint a room. Well, when I go to the store, I can't buy a partial quart. I can't buy a negative amount. I guess that would just be me giving them money and not getting anything in return. That'd be kind of silly. So that would have to be whole numbers. 0, 1, 2, 3, etc. How about the number of quarts of paint I actually use when I paint the room? Now, every time I do this, I always have some paint left in at least one can, so that's not a whole number. It's not an integer. It's got to be a rational number because there's a fractional part left. Is each statement true or false? If the statement's false, give a counterexample. Well, let's see. All integers are rational numbers. Well, all integers, let's see. 5's an integer. Can I write that as a fraction? Sure, just put a 1 on the bottom, 5 over 1. Or I could put 10 over 2. That's the same as 5. It's not reduced, but it is the same as 5. Therefore, I can write it as a fraction. So yeah, that's true. How about all negative numbers are integers? Well, let's see. All negative numbers. Well, negative 2/3 is a negative number, but it's not an integer. So I'd have to say false. And one example, counterexample, would be negative 2/3. They chose the counterexample negative 1/2. It's also a negative number, but not an integer. There are infinitely many counterexamples we could choose. We just have to pick one to prove that something's false. Every multiple of 3 is odd. Well, if I start counting by 3s, 3, 6, the second one I get to is not odd. So we'd have to say no, and 6 would be a good counterexample. No positive number is less than its absolute value. Let's think about that. No positive number is less than its absolute value. Let's see. Any positive number we can think of. 7. The absolute value, that would be 7. It's not less than that. How about 2/3? The absolute value, that would still be 2/3. That seems to be true. Yeah, that's a true statement. Write each number in the form a over b using integers to show that it's a rational number. Well, point 2. If we read that correctly, we should say 2/10 and then reduce that to 1/5. So anytime you see a decimal, just read it correctly. So you read it, write it, reduce it basically. 2/10 is what you would read. You would write 2 over 10 and you reduce it to 1/5. Read it, write it, reduce it. 5, well, that we've already heard that example. It's 5 over 1. 1.034. Let's see if we read that correctly. It's 1 and, the decimal point's the and, 34 thousandths. 1 and 34 thousandths. So that's 1,034 thousandths. We could reduce that. We probably should. What would that be? What, 517 500ths? I doubt that would go down any further. And that's our learning target for this lesson. See you in class.